Today my presentation will be about biomass gaseous fuels for engine. I try to combine two different studies because I'm trying currently to push a bit this topic in the lab, and I'm working with a composition effect of those gaseous fuel and how it impacts engine operation. So one part will be about the composition effect, the other part will be about the impurities effect in two different kinds of engine. So we can now move to the context, which will say how to decarbonize with biomass. So you all know, following the previous day's presentation, that there is an increased demand for alternative and renewable energy sources, and we need to use other energy sources with a low carbon footprint. So we can see here it's a European prospect, but anyway you can see the the use of equivalent energy and the different share of the different kind of energy. And in purple here, this is the biomass share in the energy mix, and we can see that in the next day it will increase. How do we get energy from biomass? We had a bit of presentation from Professor Van Kata on the first days. For my part, I will focus on first gasification and anaerobic digestion. From those two processes, you can get either syngas or producer gas, so mainly composed of those species. And I will especially talk about producer gas, syngas in that presentation. And those two processes can have ammonia in them, which is considered as an impurity in those processes. So basically gasifications will lead to different composition. So I will not go into detail because it's not my field of expertise, but depending on the gasifier type, the feedstocks, the pressure, the gasifying agent, etc., you can get very different compositions, so different ratios of H2, CO, and other species. And you can also have different amount of impurities, which can be ashes, tar, char, HCN, H2S, and ammonia. And we get ammonia, especially when the feedstock is nitrogenous rich. So basically when you are dealing with manure, so chicken manure, pig manure, such like this, or sewage sludge. And basically we usually remove that ammonia before burning the producer gas in a combustion process, but it has a supplementary cost. If we look at different studies in the literature, so using different feedstock and gasifier, we can see the different content of ammonia we can get in the gas. So it can be up to 6.6%, which is quite big, but that's an order of magnitude. And so we can wonder how the different composition first of the syngas can impact the operation of the engine, but also how this little quantity of ammonia can impact the process. And we can also imagine, now we know that ammonia can burn effectively in engine. What about mixing ammonia with those gaseous fuel? And Christine already showed you in her presentation the famous example of the Belgian bus using coal gas, so it's basically syngas with ammonia during the Second World War. So go back to the future and see how we can reuse those kind of mixture in engines. Okay, so how do we investigate those properties, those mixture in our laboratory? So we had a small project that enabled to find a bit the activities. So the idea is that when you have nitrogenous rich feedstock, you can either gasify them or use anaerobic digestion. From the first one you will get syngas or producer gas and a bit of ammonia. And the other one you will get biogas, so mainly methane and CO2. And you can put them into an engine to get either renewable electricity or transport for agriculture sector. And you can also combine this with renewable ammonia to get a carbon neutral energy. So the objectives of the project were to study fundamental combustion properties of biomass, various biomass fuel composition, in terms of laminar burning velocity, stretch sensitivity. I will not talk and the effect of impurities. I will not talk about that today. I will mainly focus about the engine operation, and for today I have two main parts. The first one is to study various syngas composition in a dual fuel compression ignition engine, and the second part will be a study about the ammonia effect on the syngas combustion in a spark ignition engine. So about the different mixtures we investigated, I tried to sum up those in different bar graphs. So we have 4 kinds of different syngas, as you can see here. So they are named according to the gasifier used. So the first downdraft, updraft, and free bed comes from that reference. So they are average composition, I would say, for wood gasification using different gasifier type, but they get enough variation in their composition. So, for example, you can see in green the hydrogen, in yellow the CO, gray the CO2, and blue the nitrogen. And another one, the updraft 2, is more representative of a sewage sludge gasification. And we can compare this to biogas, which is mainly 60% of methane and 40% of CO2. So you can see in terms of density, they are globally all equivalent. Regarding the air-fuel ratio, for those syngas, it's about 1 kilogram of syngas per 1 kilogram of air. Also, molar mass is almost the same. In terms of energy, so biogas and ammonia contain more energy in terms of lower heating value. The syngas are very low, but if we put that into energy per meters cube of air, so introduced in the engine, so combining the energy and the air-fuel ratio, we get almost the same, around 4 megajoule per meter cube. So once this is said, we can say that adding ammonia to those gases will not change that much. Especially for biogas, they are almost the same. If we put that into syngas, we'll have an increase in the lower heating value and a change in the stoichiometric air-fuel ratio. So now we can move to the effect of the syngas composition in the dual-fuel engine. So the work has been already published in that reference. We are reproducing the composition I introduced for those 3 gas using gas bottles and flow meters here. So they are injected through the plenum. There is no injector. And then we have a high pressure pump and an injector to inject the decaying fuel at very low pressure. So it's 200 bars. And we did different study in that work. So first, the effect of the equivalence ratio of the premix charge with a constant private fuel injection, using an optimized start of injection to get the maximum IMEP. And we also studied the effect of the decon quantity for the pilot injection, so adding more and more decane to see how we can get different performances. So these are the first results. So it is the effect of the premix equivalence ratio, so the equivalence ratio of the syngas air mixture. So you can here you can see the different compositions. So green is the updraft, red the downdraft, and blue the free bed. For different equivalence ratio, we can see that when we increase the equivalence ratio, we get higher equilibrium rate, higher peak pressure, also higher IMEP there. And basically, the downdraft gets the higher performances, and then we have the updraft and the free bed. And this is mainly related, this can be related to their hydrogen content. We get very stable combustion from equivalence ratio of 0.5, and the best is around 0.7, and we can have a very stable combustion. And the decon quantity was very low, so it's below 5% of energy, which is really interesting in terms of carbon footprint. If we look at the efficiency, we are able to get up to 40% of indicated efficiency, and for the combustion efficiency up to 98%. And as you can see, best operating range is in this area between 0.5 and 0.7 of occurrence ratio. We are also able to get very low emission. Again, the best compromise in terms of occurrence ratio is between 0.5 and 0.7 in that operating condition. So once this is say, we can see using an optical engine how the combustion is for the different composition. So you have here the conditions that are written. So all the videos are synchronized, it's the same timing. Here you have only the decaying in air, basically. And here you have the decaying plus the syngas with the same quantity of decaying in all the videos. And we can see how the syngas can affect the ignition delay. So this arrives later than this one, and we are later and later in the combustion phasing. And we can also see the change in the intensity of the flame due to the composition, and this can be going according to the hydrogen content and the methane content. So the downdraft composition has the highest hydrogen rate in the decaying, the lower. Looking at the effect of the decaying quantity, since 0.7 was the best equivalence ratio, we stick to that one, and we then increase the energy content of the pilot. So we increase the duration of the decaying injection, basically, and we can see that have a bit more diesel than the minimum required help to really decrease the combustion duration and also get higher heat release rate. For the fluid bed, we only have 2 points. It's very difficult to stabilize, so it was not possible to do the full analysis. The curve IMAP was higher, so for the next I will only focus on the downdraft and updraft composition. For the efficiency, we have up to, again, 40% of indicated efficiency for the updraft composition and almost 99% of combustion efficiency. And the best condition is for 5 to 10% of decay in energy. And if we look at the emissions, so basically the CO NOx and soot increase with the increase of decay quantity, which is logical. The unburned hydrocarbons are not that much affected. And it seems that, again, have a bit more than the minimum required is good for the combustion. So 5 to 10% of decay in energy seems to be a good compromise. So we can see that the syngas composition affect a lot the performances, and it's better to have significant hydrogen content in the mixture. We can have very low emission. It's possible to operate also with very low decaying quantity. The best compromise in terms of premix equivalence ratio was 0.7, and having a bit more decay than the minimum seems also required. So that was for the first part. I will now move to the second part, which concerns impurities effect in a spark ignition engine, published in that paper. So here we move to a single cylinder engine. With that condition, we only studied the one occurrence ratio. The composition of the syngas was this one. Why? So it's the updraft that I presented previously. Mainly because it's representative of a sewage sludge gasification, which is likely to contain ammonia. So it's very highly diluted, as you can see from the blue and the grayish here. It has a low flame speed, and in that mixture, so we mixed this syngas with ammonia from 0 to 50% in volume in the fuel blade. This is the result. So you have here the indicated mean effective pressure as function of the ammonia for two different intake pressure and the spark timing. So basically, we increase the indicated mean effective pressure with ammonia content due to the LLG and the energy input. The spark timing has to be advanced to keep the best IMAP. This is because of the flame speed of ammonia, and we were able to get very stable operation. In terms of efficiency, we have a slight decrease with the ammonia content, which can be explained partly by the increase of the combustion duration. So you have here the different combustion duration, the different phasing. And we can see that when we add ammonia, they are increasing, especially the initial phase, so between the spark timing and the 10% of mass burn. And this is mainly related to the flame speed, and we verified this using 0D kinetic simulation, so campaign simulation. And we can correlate a bit this first combustion phase with the laminar burning velocity with the ammonia content going that way here. For the emission, what happens when we have more and more ammonia in the mixture? Basically, the carbon-based emission will decrease, so CO and CO2 decrease as we are decreasing the carbon content of the fuel. Unburned hydrocarbons are not that much affected, so the dark blue bar, as you can see on the graph. The NOx in orange, they will increase as soon as we put a bit of ammonia in the blend, up to 2000 ppm. And then it is quite constant no matter what is the ammonia content in the fuel, and it seems to be related to the concentration of radicals in the mixture and maybe to the temperature. We do not have any information about N2O here because our gas analyzer was not able to measure it, so this should be investigated in further future study. If we look at the combustion efficiency, if we calculate it based only on HE and CO, we can see that it is constant. But in order to consider the possible unburned ammonia in the mixture, we had to rely on a combustion efficiency calculated on the oxygen content. And it will decrease as the percentage of ammonia increase in the mixture, so which means that we probably have unburned ammonia in the blend. And this will also make the indicated efficiency decrease. So, however, we can notice that increasing the intake pressure, so from here to here, seems to be a good way to maintain the efficiency. So, to conclude on that part, so ammonia can remain after gasification or anaerobic digestion. And basically, it is not necessary to remove it because it can burn, so we can mix it with the biomass gaseous fuel without that much impact on the combustion. But it will decrease the laminar burning velocity for sure, so probably decrease the efficiency in spark ignition engine. And it will also make the NOx surge, so which have to be taken care of, and we can get a bit of higher IMEP. So for future work, we'd like to investigate more composition, both in engine and for fundamental studies, so laminar flame speed. Also test ammonia biogas mixture, so only methane CO2 mixture mixed together with ammonia, and assess the laminar burning velocity of ammonia syngas in our vessel. So I'd like to acknowledge for the different funding organization for that project, and I'm now ready to answer any question you might have. Thank you very much.
Go to slide 5 by this.
Maybe it's better if you do it from the computer. Please, slide 5.
The bridge order example you gave, like composition of the. Yeah. So my question is actually this is for which kind of gasification, this composition, because I mean downdraft, updraft, that is fine, but it is a air gasification. Because in India now there is a lot of, because to get more hydrogen rich producer gas or finally syngas, it is going more towards the steam gasification and oxy-gasification.
So here it's air?
Yeah.
It's
so
air?
So the more, because that will be very interesting, even our institute also do a lot of work in the gasification. So steam and air gasification, in that case this composition become very different in the sense of hydrogen content. Even HC ratio become very different. It will be very interesting to study that composition now with this. That is one of the
That's very interesting indeed, so thank you for that comment. So for this study we focused on, I would say, more spread technology, and I would probably say also cheapest technology, so air air gasifier are
that
the
is
cheap.
more common for us also.
Yeah.
So that is one. Second is what that Karlsruhe Institute of Technology in Germany, they have actually commercialized already. That yesterday also I was talking about the pyrolysis oil or other bio-oil gasification. So there also H2CO ratio comes very good with respect to. So that kind of composition can be, if you can study like that.
For sure. Thank you.
See, you were saying that hydrogen rich is better. And can you tell what range you are talking about according to your study?
So here. So this is the highest hydrogen content we have. So 17% of hydrogen in the syngas bed, and this is the lowest, 9%.
Lowest.
And this was really the most difficult to stabilize.
Okay. So suppose we go more than this.
Yeah.
More hydrogen rich.
Yeah. Probably faster combustion. So easier to stabilize. If we think about spark ignition engine, you will get higher flame speed also. So normally we should have benefits.
So there will be, we can still go more, and then because I know that people are looking into some separation technology to.
Yeah, and also it has to be remained that here I really use the raw, I would say the raw composition of the producer gas. So still without the tar, char, and ashes, but in terms of gases, it's raw composition because normally you can get rid of this and have a higher lower rating value and higher performances. But here our focus was really to have, I would say, cheap gasification and plug the gasifier directly to the engine. That's what the spirit of the study.
Okay.
So this difficulty in fluidized bed stabilization was due to higher CO2 concentration or lower HP?
I mean, they are both related. So in gasification, when you have less component, you have more in others. So if for sure. So I would get a kind of balance.
And this decane was used as say surrogate fuel for.
Yeah. So here in that study, it was decane used as a surrogate for diesel. We prefer to use, I would say, a pure component fuel, so single component fuel, because after it enables us to do kinetic modeling study. Then we can have a study with Skankin, validate the mechanism of those studies, and add a deeper investigation on that.
I was just wondering about the premix equivalence ratio. What does that mean?
So I mean it is calculated only on the premix charge, meaning the syngas with the air. So it's not considering the decay in this equivalence ratio definition.
If we say equivalence ratio 1 at inlet, that means there is no sufficient air for the IFQ. Here you can see that 5 premix is 1. That means there is only sufficient air to burn the syngas, but we are adding pallet. So there must be excess air for the pallet. So I was just.
Yeah. Because globally, the global equivalence ratio. So if you consider syngas plus the decay, then you will be probably too rich.
But it's small content, so in fact, perhaps 1.1, no more, 1.05. So it's so bad that it's more similar to what you can get with a gasoline engine. It's not like diesel.
And one more question, like your pilot fuel mass was 0.11 milligram. Is it 0.11 milligram?
Am I giving I think it's written somewhere, but I do not remember. So I have indeed the.
I'm just wondering if you can, you have measured.
We measured it. In fact, we calibrate the injector. Yeah, and then we have knowing the duration, we know the mass. So I have that curve. I don't remember the.
0.1 milligram at minus 17 was enough for igniting the.
It's
0.11 milligram at minus 17 K. So is it overmixing, like it's very small mass?
Yeah.
It was able to ignite?
Yeah. So it was able to ignite for that composition. For the others, depends. But it's really the minimum. It's really the minimum required to ignite, and it's not the best condition. Okay. Thank you very much.
Long live India and France friendship.